You're welcome to Math 306 Abstract Algebra 2, and basically we'll be considering normal subgroups and cosets for chapter 1. Okay, so we'll be having like 2 videos if I'm not mistaken, but let's see how it goes for now. Okay, for the starters, things you would need to know are what we call normal subgroups, minimal normal subgroups, maximal normal subgroups, left and right cosets, and we'll consider a lemma and theorem. So we begin with definitions. The first definition you have on the screen, it says it has to do with normal subgroups, as you can see here. And what does it say? It says if you have a subgroup H in G, so let H be a subgroup of G, then this H is called a normal subgroup. H is called a normal subgroup of G if every left coset of H is again a right coset of H. Okay, so if you get the left cosets because the right cosets, you have a normal subgroup. And mathematically, this is how we write it. We write it as H is normal in G. You just see the triangle, it's this kind. Okay, so you have to be careful because they all mean different things in mathematics. Okay, so mathematically, there are 2 ways of writing it. Either you write it this way, that is, H is normal in G if and only if the left coset is equal to the right coset for all G in capital G. Or you write it as H is normal in G if and only if G inverse HG lies in capital H. Okay, so if you can write these 2 definitions, it's even sufficient. But majorly, once you're asked when is a subgroup said to be a normal subgroup, just remember that what we are looking for is that the left coset be equal to the right coset. Every left coset equals to the right coset. Okay, the next definition is what we call a minimal normal subgroup. What does it mean to be minimal? It means it has no last bonds. For instance, in a family where you have 3 kids and then there's a last born, that one will be last born in the sense that there's no other child after him or her. Is that not so? Same also with minimal. Minimal being this, there's no small element of this form between it and, okay, well, there's nobody between it and H. So K will be a minimal normal subgroup if the only person after K is this identity set, okay? And this is the after between 1 and H itself, okay? Let's take it again. Now let's take the definition properly, okay? Now we know it's just basically comparing with the last one. So if you have a subgroup H, okay, H is said to be a minimal normal subgroup of G if H is normal in G and there is no other subgroup K, you can't find it, so that it stands between 1 and H itself. Remember, H is the last one. You can't find anybody between it and the identity, okay? If you can't find that K, then H is called the minimal normal subgroup. Just like I said, for siblings, the last one is last one because there is no other person after him or her, okay? So if you can't find K, then that subgroup H is called a minimal normal subgroup. In a similar way for maximal normal subgroup, you know that between the eldest child will either be mommy or daddy, right? So if you cannot find any eldest child between them, daddy and mommy, between daddy and mommy, so let G be daddy and mommy and H be that eldest child, you can't find any M that will now come and say I am the eldest child, then that H is called a maximal normal subgroup. Okay, so let's read it as it is here. Okay, so H is a subgroup of G, then H is called a maximal normal subgroup if H is normal in G and there is no other normal subgroup M such that this relationship holds. So there's no M that can stand between H and G, where, like I said, G will be the dad and mom, okay? Next definition you need to know is what we call a quotient, okay? Now, let G be a group. You have a group, H, a normal subgroup of G, So we must have that H is a normal subgroup of G. Otherwise, you will not have this quotient. It has to be a subgroup, okay? So this quotient, G modulo H, denotes the set of left cosets of G. So the collection of all left cosets of G. How do we write that mathematically? You write it this way, okay? So remember what we said, it was normal if GH equal to HG. So left cosets equals to right cosets. Now the collection of all left cosets is written this way, okay? If you collect all of them, and when you collect them, this is how you write them mathematically, okay? Now that we know that you can collect all the cosets, is it possible that they can have a way of relating, because you can collect all of them together? Yes, they have a way of relating, and this is how they relate. If you take two left cosets and you multiply them, it's still going to be the same thing as writing, it will be the same as AB. That is, if you take AH and you multiply it by BH, the product you should get is ABH, okay? So if my A were to be, say, the identity, because you know it's a group. So if you put identity here, what do you get? That's the product. Based on that product you have there, it will be EBH. What is EB? You know E is identity, so it's just BH. So that's the product. Okay? So that's what we're saying about the property of this particular quotient group, the set of all left cosets in G. And its identity is just, the identity is just H itself, okay? So that multiplication I did, if I had written H, B, H, what would you get? Definitely you know now this is just identity. So that's like B times H straight, because this is just one when it's not written, okay? Okay, with that said, so we also have the inverse. That group also has an inverse. The inverse of this left coset G is G inverse H. Let's see if we'll get the identity back. So we have GH, we want to multiply by G inverse H, the binary operation. You all know now that this will be G inverse H, right? Because we know the product of AH times BH is AHB, is that not so? ABH, sorry. And what is G inverse G? G times G inverse by your law of groups. This is identity, so that's just H itself, that's all. And that's the answer to this product, okay? So that means that truly G inverse is the inverse of, G inverse H is the inverse of this particular group here, like this particular left coset or element, okay? Now we now know how to define the quotient group. We know what the left cosets, the set of all left cosets is, okay? There's also something we need you to know, because I'll be using that later as we continue with the course. It says the number of cosets in a group is also known as the index of the group. So when you're looking for the number of cosets in the group, so you want to know how many left cosets of this form exist in a group G. It's simply saying we want to know the index of the group. So what's the formula for that, okay? So first you know that H must be a normal subgroup. We say normal subgroup is when the left coset equals to the right coset, right? So the index is this, which is number of subgroups, is that? Number of cosets, sorry, of the group. So it's called index. It's simply the order of the group. In our own case, the group is what? We say H is a subgroup of G, is that? So the index will be the order of the group, and our group is G. That's why there's G here, the order, that's the number of elements in G, over the order of the subgroup itself, and the subgroup is H, therefore you have it here. So once you're told to define the index of a group, you're simply saying it is the order of the group, sorry, the index of a subgroup in a group G, or any group of choice, is simply saying the order of the group over the order of the subgroup. So that those are definitions you would need to know, okay? You should know them by heart. So we'll start with the first lemma. Lemma 1.4. You check your lecture notes, it should be 1.4. So it says let G be a group. So we have a group G. By now you should recall what a group is. And if you don't remember, please get your Maths 203 lecture notes and find that definition, because I will definitely ask you again. Okay, during the practical class, I will ask you. So if you have a group G and you have subgroups J and K, they're subgroup of G, it's saying that, the lemma is saying that once that happens, that this product J times K is a subgroup of G on the condition that if and only if, so we have a two-way condition from 203. So two-way condition, if and only if this product JK is equals to KJ. That is the left product. If you multiply K on the left by J, it's same as multiplying K on the right by J. So this is on, you see, it's on the left and it's on the right. So it's commutative, that is to say, is that not so? Okay, so that's the first condition once you have that property. The next one says that if J is normal, now you know what a normal subgroup is. Normal subgroup means that the left coset, so now it's G, so I shouldn't put H there, is that? In the first place, we said when H is normal, you get this, okay, not G. That the left coset equals the right coset. So in our case, it is G, so we would want to have it to be G, J, is that? Because it's no longer H now. There. So you're saying if this is normal, then this product is a subgroup of G. If you take the product of this subgroup with this normal subgroup, then this product will be a subgroup of G. So that's what it's claiming. And the final one says that if you have G is normal in G, then it is so if and only if the product of two of its cosets is again a coset. Okay, so this we would see. I have stated here that we will be proving 1 and 2, so we'll do it on the slides and the video. We'll do 1 and 2, but you students will be made to do 3. Okay, it's already solved in your lecture notes, but you are supposed to know it on your own. Okay, so go check it, find out why and know why, and if I ask you during the exercise class, be able to answer it. Okay, so let's go to the proof. So the first statement said that we should prove that if this is a subgroup, then this commutativity holds, and it's a two-way proof. So we either accept this side and show that to give us this side, or we accept this side and show it to give us this side. So let's see how it goes. I had followed strictly the lecture notes, but I'll be explaining as we go. Okay. So firstly, we are accepting that the product is a subgroup, which means we need to show commutativity. Okay. Now, if it is a subgroup, well, the subgroup means that it satisfies all the properties of a group. So this condition means this thing here satisfies all the properties of a group, meaning that it satisfies closure, it is associative, it has an inverse, and it has an identity. Okay, so JK would definitely have an inverse. It has closure, it satisfies all of that. So because of that, we want to show that JK will be equals to KJ, because that's the idea behind our proof. That's our target. So because of that, see how we went about it. Again, we know what J is. Because it satisfies the condition of a subgroup, it means it can be written this way. And now by a property you are supposed to learn in I think 300 or so, you would get it that once you have JK inverse, the same thing as saying K inverse, J inverse. It's one of the theorems, okay? So you will know that in time. But this is the rule that once you have this, because it's a subgroup, it will satisfy this, it will be same as this. But we know that this is same as this by one of the theorems or lemmas you will learn later. And because this is also a subgroup of, remember, K was a subgroup of G, and J was also a subgroup of G. And also, I can now say that this K inverse is same as K, and J inverse is the same as J, because as you had seen earlier, JK, let's write it, JK is same as JK inverse. So definitely J will be same as J inverse, and K will be same as K inverse. So that's how we got the proofs you see. So this first line. So if that is the case, so let's see something. We succeeded in showing that based on this line, that JK is same as KJ. So we're through with the first part of the proof. So that's why we stopped quickly. You understand? So the next part is the converse part, the opposite direction. So the opposite direction means we're going to accept this and prove that JK is going to be a subgroup of G. That's our target now, okay? Now, I need you to always know this, know it by heart. Whenever you are told to show that something is a subgroup, in group theory, you are expected to know this, that once you're told to show something is a subgroup, suppose it's H, I want to show that H is a subgroup of G. First thing first, confirm one, that H is not empty, okay? 2, confirm that because it is not empty, therefore, I can find X, Y in H such that such that Y inverse lies in H. That's the second thing you must do. And the third and final thing you must do, because it is not empty, okay, you can still find this X and Y. So you want to check the last stage, which is that X, Y inverse is in H. So these are 3 things you need to check. You check that H is not empty. Once it's not empty, you can find X and Y in H, and you will now check if Y inverse lies in H. Once you can do that, then you check that X, Y inverse lies in H. So in group theory, that's what we do. Once these 3 conditions are satisfied, then you can conclude that H is a subgroup of G. Again, check once you're told to find something is not empty, check that that group, whatever that group is or subgroup is, that it is not empty. Once it's not empty, because it's not empty, you can assume there are 2 elements. You could decide this is M and N. You could decide this is say F and G. Okay, so in my case here, I'm using X and Y. Okay, so using X and Y, I can find X and Y in H because H is not empty. Okay, so in that group or subgroup of your choice. Okay, so since it's not empty, you will now check if Y inverse lies in that same group. If Y inverse lies in it, wow, one more point to go. You will now check the last one, which is that this product X times Y inverse lies in that group depending on which group you are working with. So in our case, again, we are told to show, we want to confirm that we know that it is commutative because that's what we're accepting, the converse part. We have accepted that HK is equal to KH, right? So we want to prove now that this thing here, or this one, but I like this one. We want to show that this one is a subgroup of G. Okay, we want to show that. So which means we have to show that. So let's go widescreen. So we need to show that HK is what? Not empty, is that? Because that's what we just learned now. We need to show that it's not empty. We need to show because it's not empty, we can find XY in this, and we want to find that Y inverse lies in JK. And we also want to show that X inverse lies in JK. So not HK. I see I've changed it to JK here. I'm sure in your lecture notes we're using HK, okay? So don't be confused. You just lettering symbolic, just symbols, okay? I want to check these 3 conditions quickly, okay? So how do we do that? To check that JK is not empty, that one is so easy and straightforward. You know why? Because we have this relationship, JK equals to KJ. Because it cannot be equal if nothing is playing with each other in each of the sets, okay, in each of the groups. So in this one, somebody is playing, and this one, somebody is playing. That is why they are equal. So therefore, they are not empty, okay? So we have that sorted already, okay? Now that they are not empty, so that's why I said the fact that we see that JK is not empty makes it easy for us to find X and Y in K. So it means that there exists this X and Y in JK. Because if it was empty, we can't find anything, okay? So it's not empty, I can find X and Y in JK. So with that done, it means that I can prove or try to find out if this would hold, because we're at the second stage. We've done the first one, we're now at the second one. So what would that look like? We know now that JK is a subgroup. Sorry, not subgroup. We only know that individually that J and K are subgroups of G, which means they satisfy the property of a group. Is that not so? Okay. So with that said, we can easily tell that because JK, there exists X, Y in it because it's not empty. Therefore, I can take it that if Y inverse were to lie in any of them, it would be lying in this particular one, the one with the inverse. Agreed? Because this is each of them are subgroups, right? Okay, so I can do that. And I know that Y is lying in JK. Y lies in JK itself. So if it will lie in the inverse of it. But now you know, once I have this inverse, what happens? It becomes this, and this becomes, as you can see on the screen, it becomes this you have. But we know what this is. It is K. We know what this is. We know what this is. It is J. But we know by the relationship here that this thing is same as this. What does that mean? It means that we succeeded in showing that Y inverse lies in JK. Okay, you can rewind this particular part, or just rewind if I'm too fast, and try and understand. I will try and slow down too if I'm moving too fast. Okay, so again, what did we do? We went forward by showing that this was a subgroup, and then use the fact that this is a subgroup. We had this relationship. We ended up showing that this was equal to this, satisfying the commutative aspect. Now we accepted the commutative aspect, and we wanted to show that this was a subgroup. And like I said, whenever you're told to show something was a subgroup, confirm first that it's not empty. Because it's not empty, you can have this relationship and therefore prove this. And then finally check for this. So far so good. We've been able to show that it is not empty because of this relationship. And then we're able to pick this element in this Y because we know this lies in JK. And if that is the case, what happens? We'll be able to have this. You know, I'm able to write this to be this. We know now that JK is the same as JK inverse, right? Okay, so we know that. So this is same as this, and this is this, which is also this, and therefore we have this relationship. So we succeeded in showing the first two conditions for something to be a subgroup. We succeeded in proving point 1, not empty. Point 2, Y inverse lies in JK. We need to show this. So let's go to the next slide. So for this, similarly to what we had done before, we know this would lie in JK, this product of these two, right? And we know what this is. It stays this. I'm just using my hypothesis. We know that JK equal to JK, sorry, KJ, okay, commutativity. So this became this, right? You can see that. But multiplying these two together is just square of it. But if I'm multiplying them and it is square, they're all subgroups, right? It doesn't change anything. It's the same as 1. Okay, it's just like saying I am Ademola. I will still remain Ademola no matter how much you swear my name or even take it forever higher than that. I will remain Ademola. Okay, so same. So that's how we got that. This would then lie in this. That's how we got this relationship. Okay, so now you've shown this, you've shown this, you've shown this. Therefore, JK is a subgroup of G. So, the proof of the second identity, like I said, we were going to do 1 and 2. So we finished the first one. That's what it means. You can see we've concluded that. We did the first aspect of it and the second aspect, okay? Now, to prove the second part, you are doing the third part, like I said in the beginning. It's quite simple and straightforward. I'll explain why. What are we to do there? Let's find out. Let's check the statement. So we've shown this. We're now at this one. You are doing this one. So we want to accept that J is normal and then prove that JK is a subgroup. Now you want to say, should we not check that J is not empty, all of those clauses? Let's see if we are, I don't think we necessarily have to do that because of the fact that we've been able to show a relationship in this form. Okay, so let's see the relationship, shall we? Okay. So for this one, very easy. Since J is normal in G. What does that mean? It means that you can do this. GJ, remember the definition for something being normal is same as JG. Is that true? When the definition of being normal. Oh, okay, so I'm beginning to have a relationship here. Is that not so? Now, G is an element in capital G and it's for every element of G. All. it allows that. But we already know that K is a subgroup of G, is that not so? And we said this G is every element of G, which means G is also in K. Do you agree? Everything. Every time you pick an element of G, this thing will hold here. So that's what he's saying. But K is a subgroup of G, which means G must lie in K. They are from the same basket. Pull everything from the same basket. Okay, everything's in the same basket. Like saying you have a basket of balls. All of them are balls. Red balls and blue balls. Okay? Let the blue balls be J and the red balls be K. However you do, whenever J relates as a normal subgroup, it will take any G, red or blue, and play with them. Anyhow, commutativity holds. And that's what I'm saying. Whether blue ball, red ball. But K is in that, which means that whatever ball I pick will satisfy this, right? Which means that I can write it that Kj will be equals to Jk. Because for any G, any ball I pick, J will play with it however you do it. So that relationship holds. So let's explain what you see up here, which I've written up here, so that you understand. So that's the way of viewing it in your mind. How do we write it down? So writing it looks like this. Since J is normal in G, it follows from the definition of a normal subgroup that for all G, that this relationship holds, right? And since K is a subgroup of G, it is clear that this would hold. That's just simply what I explained, that I wrote down here before now. Okay? Okay, so that's the completion. That completes the first and second part of the lemma. And now we go into a theorem. And the theorem states that let G be a group. H and K are finite subgroups of G. So you have a group G, and H and K are finite, which means you can count the number of elements in both of them, H and K. They are subgroups of G. Then the number of the product HK, so this order, is same as this fraction. That's the order of H times the order of K over the order of H intersection K. Okay, so that's what they're saying. So you have a group, you have we have two finite subgroups, and they're saying this relationship holds. This relationship holds for both of them. Okay, so how do we prove this? Okay, so first thing first, once you have subgroups and you have something like an intersection of them, you want to consider how they relate based on cosets, okay? And once you have this kind of intersection, it is obvious that this will be a subgroup of K. Is that true? The intersection between H and K. Because it brings in all the elements that are in K and all the elements that are in H, right? So definitely this will be subgroup of K. So this intersection, it will partition K. How do we mean? It's like saying you have a big box, and the intersection is just taking one small part. It will just be relating all the elements in K. So this is all of K. We're playing with it and breaking it into small bits. So you can partition and break it into small sections, okay? So H intersection, the intersection can do that with all of the Ks. So if this is to be K1, K2, K3, H can play with all of them, okay? And that allows for partitioning. So if I'm not being so clear, but that's what happens when you're working with intersection and when you're working with cosets. Cosets actually partitions your entire group or subgroups, okay? So it can partition K. So if it partitions K, we are saying, okay, let's set D to because the H intersection K, just for ease of our solutions, okay? So K can be expressed as this. Remember I was saying that H intersection K can partition K into small partitions, okay? So if we follow that, this D now is this intersection, okay? So it will partition, is playing with them. Because if you take the union of all these small boxes, you should get back K, right? Okay? So let me start from the top now. So the biggest of relationship or most complex is this one, okay, because of the intersection. We're saying that the intersection will make H intersection K a subgroup of K. Same also, it definitely will be a subgroup of H, but we're interested in the K. You will see why as we continue, okay? Okay, so H intersection K is a subgroup of K, and we know that this intersection will partition K. And we now set D to be equal to the H intersection K. And we can express K in this way because of the partitioning into small bits of big K by the intersection, okay? And the relationship of cosets. Okay, we know what the K's are. They're the small partitionings, okay? And the elements of capital K, okay? Now, if you recall the definition, under definitions, we had defined the index of H and K. What was it, if you remember? We said it's the order of the group over the order of the subgroup. If you don't remember, you can go back and find it. But this is it here, recall that this is what it says, the index. We're bringing in the index because it's the closest to bringing the order of G and the order of elements, you can see. Because this is what we're based on this, and based on this, you can see that we will need that index thing. Okay. With that said, there are n cosets in K. How did we know that? Remember again that H and K are what? Are finite subgroups. And we saw that this intersection will partition it, right? And we set it to be D. We were able to see we label our partitions and stopped at n. We don't know what n is. N could be 1,000. N could even be 20. We don't know. But because we're working arbitrarily, we have said let it be called n, okay? So we stopped at n in our partitioning. N could be any number, okay? We are using the concept of the index to work right now. So now we know there are n cosets based on the partitioning we have seen there. So, and we know that H intersection K is a subgroup of capital K. So based on this definition of index, let me clean my screen. It's getting too cumbersome. So let's take it again from the top, or not too far. So we know H intersection K is a subgroup based on this definition. Our subgroup is this. So this will now be using this two. Our group is G. In our own case, our group is H. Okay, so how would that look now? The index, we know there are n of them. That's why there's n right here to index of H intersection K. Our group is K, so the order is K. And what is H? H is this subgroup, right? So that's why there's order of H intersection K. Let me go over it again so you see it. Again, we started by considering this denominator. And we know that H intersection K obviously is a subgroup of the K itself. And we saw that this H intersection K will partition K. And it broke in such a way that if we set H intersection K to be D, we'll have this relationship based on union. Is that not so? And I said that we're not sure of the number of boxes H was broken into partitions, okay? Since we're not sure, we called it N because it was arbitrary. So having chosen N, we know that that will be the number of subgroups or relationship this H intersection K has with elements in capital K. Okay, so we want to find the index, right, of H. And in our own case, the index we're looking for is the index of this. So what is the index of this? It's simply this over the order of the group, and our group is this, and over the order of the subgroup, and our subgroup is this. Is that not so? So what is the index? There were n of them, so that's why there's n here. We're going to be looking for the order of K. There's the order of K, and the order of H intersection K, which is this, because it is the subgroup, remember? H is a subgroup of G, and in our case here, it is K, sorry. In our case here, this is our relationship. So we're just comparing these two, okay, to get our relationship. Okay, so now we have a relationship, and it's almost looking like what we're looking for here, right? See, up here we have almost. We still need to find some other things that are missing. So let's see how to move and bring it in. Okay, so we'll move forward. Now the goal is to find this. Is that also it says we're looking for the order of H, K. We want to find it, and we want to prove that it's going to be the order of H over the order of K all over the order of H intersection K. That's what we want to show. We need to find this. But we've been able to show that N is equal to the order of K all over the order of H intersection K thus far, okay? We haven't been able to bring in this and this. So let's see how to bring it in, okay? So our goal is to find that, but we know before from the previous slide, we know that there's a relationship in K. This relationship here. We have this relationship. If I bring in H and multiply H all through this relationship, let's put H in between, multiply H up here, sorry, H here, and H goes through. Let's see what that will look like. So that's what we're going to do next there. So the relationship which you saw, K, which is this, if I bring in K all through, so K will be in front here and all over each of them, the terms there. You see, H comes in, H comes in. But HD, what is D again? You know D is H intersection K, right? And you know that as much as H intersection K is a subgroup of K, it's also a subgroup of H. Is that true? Because every element in H is also going to be in H intersection K, right? Okay, so it's the same thing. So therefore, if I take that, it means if I do D times H, I'm basically getting back H, just lumping them because it's the elements that are in H that are also in H intersection K. So if you multiply them together, I'm going to get back that. That's how we got this relationship here. Okay, that's how we got all of that you see there. Okay, let's move. So the product of this gives you this, which you have there. And I give you the reason why there. So if I want to add them together, remember what union is. Another way of doing is addition, is that? So if you change all, because I want to find the order now. If I put the order there, what happens? It will become HK1 plus HK2 all the way to HKN, right? Okay, so let's continue. Now you know how many K's we have. There are n of them, right? We gave it an assumption. We said we don't know how many, so we stopped at n. So there are n of them. N could be any number. So if there are n of them, what happens? There are K1, K2, all the way to Kn, and H is just following. And H is a what? It's a subgroup. So basically I have n of the K's times the order of H, meaning that I have the order of H, K, to be equal to N, H. Oh, but you know N, don't you? In the previous slide, we had found N. What is N? We had found N. It is this here. Okay? So we know now that the product of the order of H, K is N times the order of H, which is what you see. Where did I write it? Okay, well, I didn't write it down clearly, but this relationship gave us this here. This relationship. So I know this relationship. What do? I know what one n is. N is this. So I just substitute back wherever I see n. So n, I substitute back n. What is n? Is the order of K over the order of H intersection K. So this is n. I bring in my substitution, and if you multiply it properly, just arrange it, rearrange it, you get this. And that's onto the proof. Okay, so you could go through over the video again, write it out on your own, practice and see. If you have any question on the WhatsApp group, you can post your questions. Okay, thank you very much.